4.4 Day 9 Notes. Compound interest is our topic. So for those of you that plan to do any investing or take out any loans, this may be of interest to you especially. So the first case, if we think about like a simple interest that's done annually, that's exactly our exponential function we've looked at. So that's a really simple case for something that we've already done. So that's like A would be our initial amount, B would be our growth factor, and then X would be like how many times it's actually compounded. Okay, so that's like the really easy way that you can think about it. But then a little bit more advanced would be like compound interest. So whether it's compounded quarterly or monthly or even daily, we use this formula. So it's B equals P times 1 plus R over N to the power of NT. And some of those variables you probably already know. So, for example, P, that's the initial investment, otherwise known as the principal. P is the initial investment in the account, otherwise known as the principal. That's the thing that we're hoping is going to grow. Okay, so that's P. R, that's actually just our annual interest rate. Another word for that is like the nominal rate. We'll talk about that in a second. N, that's the number of times it gets compounded. So if it's monthly, N would be 12. And then T, that's the number of years. That's time, basically. And it's measured in number of years. And then what would be a good thing for B? Well, B, that can just represent like the balance in our account when we're all done. We're all said and done. What's the balance in our account after T years? Okay, so simple interest, that looks like an exponential function. Like you got your starting amount, A, and then the multiplier, B, that's your growth factor, and then how many times is X. And then this is compound interest. So, our first example, you invest $1,000 at an annual interest rate of 12%. What's the account balance after 1 year if it's compounded? So I haven't told you how it's going to be compounded yet, but this is what we got so far. $1,000, annual interest rate's 12%. We're going to find the account balance after 1 year, and then the first case we're going to do, part A, is compounded annually. So this one's actually pretty simple. Annually means you compound it once, like every year. That's when you compound it. So if it's only in there for 1 year, and you compound it once annually, you basically are going to earn 12%. Let's show that. So you increase by 12% a year. So your growth factor, if you increase 12%, if you're growing 12%, so it's basically just 1 plus 0.12, or just 1.12. So if you multiply your bank account by 1.12, that means you increase 12%. So the balance in our account would be $1,000, that's our starting value, times 1.12, and that only happens once. We're only doing it for 1 year. So it's compounded annually one time. So you multiply that together, you get $1,120. And notice, like, we could have used the compound interest formula, but it would have been a little bit excessive to plug in like 1 for T and 1 for N. This ends up looking a lot like just the simple exponential formula. Okay, so that's a bit of an easy one. How about part B? Let's compound it monthly. So same investment. What if you compound it monthly? Well, let's go ahead and just plug it into the formula. So our initial investment was $1,000, so that's P. And then we have 1 plus, well, R, the interest rate would be 12%, so 0.12. Monthly means N would be 12, so I'll put an N, like where N is, I'll put 12. And then how many times is it compounded? That's what goes up here. So N times T means how many times it's going to be compounded. So if it's 1 year and 12 months, that's 12 times 1. just 12 times. So in the exponent, that's how many times it gets compounded. So that's 1,000 times 1.01 to the 12, which is 1,000 times 1.26825. So did this earn exactly 12% interest? No, it didn't. Look, this definitely earns more than this one. So monthly looks like it's going to earn more interest in the long run than this one. Just look at the growth factor here. 1.126825. That's a bigger number than 1.12. So this is, the total is 1,000. I mean, just move the decimal place a couple, or 3 spaces basically, right? So $1,126.83. But I want to talk about this interest rate for just a second. So this is like the effective, this is called the effective annual yield. So 12%, yeah, that's the interest rate we were given, but the fact that it was compounded monthly means we actually earned a little more. So effectively, what was the annual yield? What was the annual rate that we earned? It was this. So we say this has an effective annual yield of 12.6825%. The same goes for this one. This effective yield was just 12%. So it didn't have any difference from the given interest rate. Effective annual yield for this guy was still 12%. So the interest that we actually earn after it gets compounded, that's the effective annual yield. This interest rate that we're given to start with, that's actually called the nominal rate. And when you think of nominal, I'm going to give you a cue to remember that. That means in name only. So when you're going to invest money or take out a loan, the nominal rate is just the interest rate that's in the name only. So yeah, it says 12%, but in this case, we effectively earned more than that. This case we didn't because it was only compounded once at 12%. So in this case, the effective annual yield would be the same as the nominal rate. But in part B, the effective rate's actually a little bit higher because it's compounded more. Okay, example 2. Similar setup. You invest $1,000 at an annual interest rate of 6% this time. What's the account balance after 5 years? And this time, I want it compounded monthly. So this one, if you follow the last one pretty well, this one should actually be pretty easy. We can go ahead and throw it in the formula. The account balance, the starting amount, the initial investment was $1,000, so 1 plus, and then R in this case, the nominal rate we're given here is 6%, so that's 0.06. It's compounded monthly, so that would mean N equals 12 times. And then for 5 years, if it's compounded monthly, that should be a total of 60 times it gets compounded, because 5 times 12, that gives you 60. So what's the account balance here? Well, this is 1,000 times 1.005 to the 60 if you simplify it, or $1,348.85. So it looks like as long as you put the values in correctly, your calculator, like things are set up correctly, this is not too bad. Okay, in example 3, I want to do a really similar case. So a $1,000 investment at an annual interest rate of 6%. But now I want to know the balance after 6 months. And this one's actually compounded quarterly. So a little different setup, but again, if you follow the formula well, this should be no problem. So the balance after 6 months, so half a year. And this one's actually compounded quarterly, so 4 times a year. Okay, so let's start with B equals the initial investment, 1 plus, and then the interest rate again is 0.06. And then N in this case, if it's compounded quarterly, that means N equals 4. So that's how many times it gets compounded in a year. 6 months, So in terms of time, that's half a year. So t should be 1/2 in this case. 6 months is just half a year. So in 1 year, or in 6 months, how many times does it get compounded? 1/2 times 4, that's going to be 2. Which should make sense. Compounded quarterly, there's 2 quarters in a half. So that should make sense. So simplify this a little bit. 1.015 to the power of 2, which gives us approximately $1,030.23. So I guess the real unique thing about this one was the fact that it was only 6 months, so you had to use 1/2 for t as your year. All right, example 4. You deposit P dollars. I didn't tell you what P was, but you deposit P dollars in an account paying interest at the nominal rate of 4% per year. And this gets compounded quarterly. So I haven't even asked a question yet, so here's the question. By what factor does P grow in 3 years? And I'll give you a hint, it's not 4%. Right? That's only the nominal rate. That's where we start out at. That doesn't take into account all the times that we compound it and so forth. So let's just set up the equation, and we'll just leave P as a variable. So our balance equals the initial investment's P. We don't know what it is. That's okay. Just leave it as P. And then 1 plus our rate of 4%, so 0.04. It's compounded quarterly, so that's 4 times a year, so N equals 4. And then 3 years, so that should be 12 up here, because this is N times T. Okay, so then the only math we have to do here is just to simplify this piece. So we got P times 1.126825. So all I did was I did 1 plus 0.04 over 4, and I took that to the 12th power, and this is where I'm at. So now you can answer the question, what's the factor that P grows by? What factor does P grow by in those 3 years? Well, it's this, P times this thing. So now we can answer the question. After 3 years, the initial deposit, P, it grows by a factor of 1.126825. So basically, it was multiplied by 112%. Okay, so that's a unique example where I didn't give you the initial investment amount, but you just use P, and you find the growth factor, basically. You find the B value. Notice that looks like the B value from exponential functions. So that's the growth factor here. Okay, and then one more example for the road. I want to make sure you know the difference between nominal rate, so that's just the in name only. So that's just what you're given to start out with. That's not typically the rate that you're left with at the end. So versus the effective annual yield, or another name for that you'll see is just the effective yield, or another really common one is APY. So that's annual percentage yield. So those all mean the same thing. Or if you saw this as like effective annual rate or effective rate, they mean the same thing also. So 2 different things. Nominal rate is what you're given to begin with. It's just in the name. The effective annual yield is what you would effectively earn, like the rate you would effectively earn after a year and after all its compounding. So then my last example here, example 5. What is the effective annual yield if a deposit of $2,000 grows to $7,000 in 15 years? So this one I want to actually relate back to basic exponential functions. Your initial amount is 2,000 and it grows to 7,000 in 15 years. What was the effective annual yield? So basically, what was it growing by each year? So I want to set it up that way then. If it's like a basic exponential function, it's like A equals 2,000. We don't know what the multiplier is. We don't know what B is. But we know it goes 15 years. It happens 15 times that it gets multiplied by. So we just don't know the growth factor, so I'm going to leave it as B. So initial investment multiplied by B to the 15, and it should, at the end of those 15 years, be $7,000. So now we have an equation. If you solve for B, you could tell me what the effective annual yield was. So that's actually pretty simple here. Divide by 2,000. Let's try to get to B. And I've got B to the 15th equals 3.5. That's actually really easy division there. 7 divided by 2, essentially. So just take the 15th root of both sides. And B is about 1.0871. So that would be the growth factor. That's how much it grew by each year, like the multiplier. But the effective annual yield, that's the percentage that's bigger than 1. So if you do 1.0871 and then subtract 1 from it, that's the effective annual yield, or the effective annual rate that you were growing at. So in this case, the effective annual yield over the 15-year period is just that 8.71%. So that's the growth rate. Like example 4, it asked for like what the growth rate was, like this whole 1.0 answer. And now it asks for the effective annual yield, or the effective annual rate. So that's how much bigger this is than 1. What's the leftover? How much bigger is it than 100%? 8.71%. All right, that's all for these notes. I'll see you in class.